applications, and because it's a workshop on communication complexity, I'm going to talk about an application in the communication complexity of decoding. It's a joint work with Lad Haramati, who was a postdoc at Northeastern, and he went to Harvard, and now he's in Israel. My student, Chino Lee. There's actually a few papers, so it's mostly this work with Haramati and Lee, and then another one by Lee and myself, and Lee is on the job market for next year. He's very good. A distribution D on m bits is t-wise independent if any t bits are uniform. Okay, it's a very basic notion that was around since at least Carter and Wegman. And thanks to a long line of research, it's known that these distributions fool, in this sense that I'm going to go through in a second, several classes of interest. So for example, there was a breakthrough and incomprehensible result by Basi that shows that with polylogarithmic t, such distributions look random to DNF. Okay? This was a very nice result, which was then simplified by Ratzborov and extended by Breman to AC0. And you can do similar things for other classes. There is this paper with Diakonicolas, Gopala, and Jaiswal and Servedian, which we show it for polynomial threshold functions. Of degree 1, and again it was extended to a higher degree, okay, and there's more results. By full, here I mean that the expectation of any function in these classes over the distribution D is close to the expectation of a uniform. Okay, so it fools a lot of stuff, but there is one simple function which you all know that is not fooled by these things, which is parity. Thank you. So it does not fool parity. Okay, but you can tweak it a little bit, D, and then it fools parity. So you can add some noise to D. Okay? So what I mean by noise, so I'm going to denote by capital N a noise vector of I and D bits, and each bit is one, and we say probably 1 over 10, okay, or 1 over 100. And the main object of interest in this talk is what you get by the bitwise XOR of D and N, D plus N. Okay? So it's the fact that D plus N actually fools parity. Okay? So let's say I mean by parity the parity on any subset of the bits. Okay? So it could be 1 bit, in which case you need, it is just fooled by D, okay? But if it's many bits, actually you need noise.
So is it clear that like just noise wouldn't fool parity?
Right. So good. So as I say, so you actually need both D and N. So if it's a parity on just 1 bit, then noise is not sufficient. Okay, it will give you error 1 over 100, which is not good enough. Okay? So if you want to get error epsilon, actually you need both D and N. And in all of our examples, it will be the case that it's really the combination of D and N, which is important. It doesn't work with either D or N. So a very interesting question is what is fooled by D plus N? Okay? And this question actually goes back to a work by Atai and Widerson, and then was later revived in a very nice work by Gopalan, Mecca, Rangel, Trevisan, and Badan, but they think of it in a different way. They don't talk about binary balance plus noise. So I think the first work that discusses things in these terms is this one. So which model is fooled by binary balance plus noise? It's a good question. And I want to stress that it's a special case of other questions which are floating around. So for example, we have seen in the last workshop some very nice result about fooling functions via random walks, okay? And what they need for that is a condition, the Fourier growth of the functions. So if you have a Fourier growth, it implies that also D plus N fools it, okay? Okay, so what we show, so the main result that I want to mention is something which extends this simple parity effect, in which we spent a lot of time thinking about, starting 3 years ago, the Simon's workshop here. So is this result here? Okay. So it's an extension of this fact about parity for functions on for arbitrary functions. Okay. So the setup is that you have k functions. So k is another parameter now. F1, F2, Fk. These are function L bits. Okay, and they're bounded. You can think of it as just a -1, 1 if you want. And then you look at the product of these functions. Okay, so it's a product test. So it's a function f, which now is over L times k bits. Okay, and the output is bounded again. So the value of f on a k tuple is just the product of the f. So f1 on x1 times f2 on x2, and so on. Okay? So I want to claim that this function here is fooled by d plus n. So you have some required condition on t, so t has to be at least about L, okay? Because if t is less than L, then essentially just one function can tell the distribution from your, okay? Up to some correction with the noise, but it doesn't matter. So let's say that t is at least 10 times L, and then I claim it fools. So what error bound can we hope for here? So what's the best possible error bound that you could hope for? So this thing could be a parity on t plus 1 bits. What would be the error in the case? What would be the error if it's a parity on t plus 1 bits? So d could do nothing for you. So it would just be just the noise. So it would be exponentially smaller in t. And that's what you get. Okay, so the error here is this. And this thing is tight just because of parity. You can write the parity as a product of these functions. Does it make sense?
T is not T over L there.
Just T, yeah. This thing, yeah. And this thing is tight because so in particular I don't have any dependence on k, which is nice. So who proved this bound? So there was this paper by Emanuele and Viola which showed something which is good, but only unfortunately when k is small. This paper took us a great of effort. Then there is another paper with 3 in which we have large k, but the bound unfortunately is not that good. But it's a worse bound. And then there is a very nice paper by Forbes and Kelly, which I think it was just in this last StockFox anyway, just came up online, in which they take the Emanuele and Viola and they modify it a little bit in a very nice way, and they essentially get this bound. Get something a little bit worse. They have k. So it's not written there, but it implies a bound form k times 2 to the minus omega t. So they still have a dependence on k, but you can just use a simple idea from Lee and Viola to remove it. So if you combine this and that, you will get this bound here. So I'll tell you in a bit what's the proof of that. Well, somebody has seen the proof. Before that, I want to say something about applications. So these things actually have several applications. So one set of applications in there are pseudo-randomness. So I'm mentioning this connection with Fourier growth, but basically you can use these type of results to get pseudo-random generators for branching programs. The Forbes and Kelly paper essentially matches the so Nissan has this log-standing generator in which you can fool branching programs in a fixed order. They can essentially do the same thing in arbitrary order, which is very nice. And in addition to that, there is also a very nice paper online by Mecca, Reingold, and Tal, in which they do pseudo-random generator for with 3 branching programs. So they also use ideas from these papers. Some of the analysis is taken from here, in addition to many other things. But today I want to stress this consequence for communication complexity. Okay, and there seem to be some more applications coming out. Okay, so let's move to communication complexity. So the setting is that of error correcting codes. Let me start with a question for you. What's harder? Encoding or decoding? What do you think? Decoding. Can you prove it? So it seems like decoding is harder. Like, can you prove it? Can anyone say one model in which you can prove that decoding is harder than encoding? I don't know it. Can you encode in net zero? No, because you can just flip a bit and then you don't have a distance. Can you decode? As far as I know, it's open. It's not known if you can decode in net zero. Okay, so some motivation of actually proving a result along these lines. So I'm going to give you a setting in which decoding is harder. Okay, the communication complexity setting. Yeah. So the communication complexity, some streaming questions were asked already, but they couldn't say anything more about decoding than encoding. Okay, which is that they both are somewhat hard for streaming or things like that. Okay, so what's the setup? All right, so here's our setup. So for simplicity, I'm just going to state things for Ritz-Solomon codes. So I have a Ritz-Solomon code over some alphabet FQ, block length M. Okay. So for this result, I will need to generalize this to not to bits, but to arbitrary alphabets. And I will also need generalization in which the rate of the error is taken into account, which is not written here, but it follows along the same lines. Okay. So your Ritz-Solomon code, so let's say this thing has dimension, let's say M, where k, so k is another parameter, let's say k is like 100. So as dimension m over 100, and I need a little bit more, you can actually essentially remove this constant, but let me just put a 10 here. Okay, so then there is a received word with some number e of errors. Okay, so there is a received word here, and this word now is split among k parties. Okay, so it's split among k parties. Okay, so it's split in just a number in hand. Okay, so party I just knows this, party 2 just knows that, and so on. And these parties communicate to decode one message symbol. Okay, so this is clear, and you want to know how much they have to communicate for that, just to decode one symbol. Okay, and the theorem is that the communication is theta t tilde because I'm going to ignore some logs of E. Okay? So the amount of communication is just the number of errors, and this thing is tight.
What's the relation between E and K in this?
Right. So good. So let me think of K as just some fixed constants, and so let's say K is like 1,000,000. Then of course, so for this to make sense, it has to be decodable at all. So actually, E can't become linear with M. So let's say just E is like, between 0 and 1/1,000,000,000 or something. Does that answer the question? Okay. So you can actually generalize this to smaller K, but I'm just going to think of a K as being a constant for now. But okay, so actually, to better answer your question, there's no relationship. So the bound is just in terms of E, just in terms of the number of errors. I think it holds now with this Forbes and Kelly result. It holds even for even for a very large K, you can actually get that. Yeah. So I think actually.
So in particular, O tilde E is possible, I guess you're saying theta, so that's like both upper bound and lower bound.
Yeah, yes, the upper bound. Yeah. So the upper bound is just it's a very simple thing, and the lower bound comes from this. So actually, let me give you the proof sketch of this, so that you can see how I use that theorem. Actually, before that, just a note that. So if you just want to compute one symbol of the encoding, it would just be constant communication. Okay, so in this sense, if you find it satisfactory, it shows that the decoding is more complicated. Okay, so the proof sketch, I'm just going to sketch it to show you how the pieces get together. But so by the way, so actually some symbols are very easy to decode. So what I mean here is that there exists, actually, for most symbols, it would be difficult, okay, or for a given symbol. So, so if you fix a message symbol, okay, so for most symbols, you have you just decrease the dimension by 1. So you have 10 M/K-1 Reed-Solomon code. Okay, for some symbols to fix, maybe not all. So such codes, so it's known that a uniform code word is this much independent. Okay, so this thing is my value of t. Is how much event. This is just because a random line goes to any 2 points with the same probability. So that means that if you now think of the noise as being uniform, the parties won't be able to distinguish a uniform code word from this thing and noise. And this thing holds for any possible way in which I could have fixed its message symbol, which means that actually they have no information of what the message symbol is. Make sense?
What class are you fooling with this?
I'm fooling communication protocols. Oh yeah, sorry. Maybe I should put an line. Yeah. So a K-party protocol, is a union of products. Okay. So the number of products. So products mean of tests of this type. So the number of products would be its exponential in the communication. So you will need to prove an error which depends on the error rate to get this bound, which it's an extension of that. Yeah. So that's how you get the lower bound. Okay. Okay. So I'm gonna.
So the lower bound that you're getting out of this is t bits of communication are needed if you had this.
So this lower bound has to be generalized
Q
with the error. No, Q doesn't matter with the error rate. So it's so the lower bound has to this error here has to depend on the noise rate. So it would be So I'm going to show you the proof of this theorem now. And actually, I wanted to show you this Forbes and Kelly extension, but then even though it's very simple, somehow it's not so intuitive for me to explain it in 2 minutes. So I'm going to go back to the previous one and tell you some ideas of how you can extend it. So here was this is the basic idea in the previous result. By the way, the previous result already is sufficient to get these bounds for quotes for say for constant k, or even a bit larger. So proof idea. Okay, so here's the basic idea. Let's look at the case of k equals 3 for simplicity. So we are looking at f1, f2, f3. Okay? And so the basic idea is this. So let me write f3 as f3h plus f3l. So I should say at the beginning that the basic idea, just like with parity, is that the noise will fool. So we're going to use some Fourier analysis, and the noise will fool the high Fourier coefficients, and the boundary variance will fool the small Fourier coefficients. But formalizing this somehow is not so straightforward. So here is a way in which you can do it. So you're going to decompose f3 in the sum of f3h and f3l, and f3h has the high Fourier coefficients, and f3l has a low, a small. Okay, and if I do this and I plug it here, then I get that, so this is my f. My f now becomes f1 times f2 times f3h plus f1, f2, f3l. Okay? And now I'm going to, it was natural to us, and now let's keep doing that. Okay? I'm just going to do this thing again here. Actually, I'll tell you in a second why. So you continue that. So I'm going to keep this, f1, f2, f3h. Then I'm going to have this thing. I'm going to have f1, f2, sorry, f1, f2h, f3l. And then I'm going to have f1, f2l, f3l. Okay, so I just decompose f2. And then I'm going to repeat the process here. So I'm just going to, for simplicity, erase this and open up f. So what you get here is f1h, f2l, f3l, plus f1l, f2l, f3l. Okay. So now, this is just the product of low Fourier coefficients. So if the threshold that you picked here is t over 3, and you have ty invariance, then this thing is just followed by d. Followed by d. Okay. And the idea is that each of these factors is fooled by d plus n. Actually, for these things, you need both d and n. Let me just show you in a minute how you can do that. Okay, and some part of the complication is that for us is that f3l may not be bounded. It's some truncation of a bounded function, but it may not be bounded. But it doesn't matter. So you're looking at the expectation of, let's say, let me do one term. Let me just do this one, right? F1h, F2l, F3l. So let me call these things here G. So I'm looking at the expectation of F1H, and then G. Okay, so this is the expectation over D plus N. Okay, so the noise is uniform. That's nice. So I can bring it inside. So I have expectation over D of the expectation over noise of F1H. I should put the input. So this is the part of D which belongs to F1. So D1 plus N. Okay, and then times the expectation over N of G, let's say D2 plus N. Okay. So I haven't done anything, just bring inside the noise. Now, you know, you can do Cauchy-Schwarz and to decouple these two things. So you will get the expectation of D of the expectation over N square of F1H D plus N. Okay? And some other stuff here, expectation over D of these things here. Now G has low degree, so even if you square it, it's still going to have low degree. It's going to be twice the degree. So if you set the parameter side, this thing is small just by D. Okay? So I'm going to, I'm not going to, so I'm not going to worry about this. Okay? So maybe it's not really clear. But anyway, I'm going to ignore that term. Now, essentially, just because this thing has high Fourier coefficients, the noise part will fall it. Okay? So D is useful because it takes care of the square here. So I'm not going to allow also B squared. So this thing is small. So the error here will be the size of the threshold that you picked here.
So not only is it fully neat, it's also small.
Okay, yes. So actually the fooling, so here fooling means that you will get what you want, the zero Fourier coefficient, and then anything else will be small. So the Forbes and Cagliacci is a very similar idea. They decompose the function in things like this with a high Fourier coefficient and low Fourier coefficient part. Again, they use exactly this reasoning. But while in our case, it seems that every decomposition you lose a little bit in degree, so you couldn't repeat these things more than t times if you even these things just getting one. Somehow they have a different way of grouping the Fourier coefficients, which allows them to repeat more often. That's it. Thank you.
What's a function that's not fooled?
That's a fantastic question. Actually, I spent the last X years of my life thinking about this. And what's a function that's not fooled by D plus N? I spent like an enormous amount of time on it. Not that it means anything, but still I spent it. We don't know. So the best that we can show, so for example, for polynomial size circuits, you actually, it's not full. You will need, you can prove type bounds. You need the exponential parameters to full polynomial size circuits, and you can push this to like NC2. But even showing that, I don't know, NC1 or like KC0. So just to be concrete, for example, can you fool, does order of log n wise independence plus noise full AC0? I spent a lot of time on this, but I don't know how to do it in a way.
What's the simplest function that does fool? there's,
The simplest function which I know that requires super polynomial parameters in some sense lies, I believe, in NC2. NC2, I think.
I mean, does it have a simple description or?
Oh yeah, so yes, so one reason why, thank you. One reason why I'm going to this, so it's just, it's decoding, right? So if you can give me a code that you can decode, yeah, thank you, I should mention that. If you give me a code that you can decode, then you break this, and you can decode Reed-Solomon codes in NC2. I don't know how to decode Reed-Solomon codes in NC1. If anyone knows, I will be very happy. I think NC2, so it's just inverting system.
Right. So you want to not be solving the determinant or whatever.
Okay, I don't know, right, so it's essentially it's in one of those classes like that or something. I don't know how to do, so I don't know how to do it in substantially global classes. It will be very interesting to me.
You should do polar codes.
What then?
Polar codes.
So do they? I mean,
you need the code to be of sufficient distance, I suspect.
yes, so it has to be a code of dual distance. So
But you will probably have something, yeah.
and those are decodable in.
Looks like an FFT, so it should be NC1.
Okay, but over binary, so okay, so you should, okay, that's very interesting. Yeah, so actually I looked at those, but I couldn't. Yeah.
I forget, so Bossy's result, how many bits does he need for, how many wise independent?
So polylog, so I think it's like log
Yeah, but
cube.
so does order log, can you do that for DNF?
It's not known.
You don't know?
It's a fantastic question. I don't know. So we know that, which is not obvious, so we have a result which says that you do need omega log n for DNF. So it's not completely obvious that this thing, you need omega log n for DNF, but I don't know if you need more than that. Omega log n, like maybe order log n plus noise folds DNF. I think, I don't know if anyone here has a sense. I think, yeah, I don't know.
So I missed something earlier. Why did you say that the communication protocol is a union of products of different products?
Oh, I'm not doing anything fancy, so it's just that, so it's like communication is rectangles, right? So a product, so think of this as a rectangle, just think of it like 0, 1. This is the characteristic function of a k-dimensional rectangle. This is number in hand, so for k equals 2, this thing is just rectangles. For k equals 3, it becomes cubes, and so on. Does it? Think of this as just the characteristic function of a rectangle for k equals 2, and you can write any protocol just summing over transcript. You can write this as so that's what I'm doing. Square brackets. Oh, here. Oh, yeah, no. So you don't need this. So I'm doing this. So yeah, for communication complexity, you would just need this. Yes, you would just need this. But in fact, all this stuff, you can actually do all this over C1, which has some consequences for some strange classes of tests. But, yeah. But you would just need 0, 1 for communication. Yeah.
More questions?
Thanks.